Booklet 3, question 7, booklet 3, question 1. Okay, fine. Booklet 3 has been talked about first, so let's have a look at that, um, which is here. Okay, let's have a look for the first question first. Which component is a variable resistor? Okay, so if you didn't do this in the lesson, then unfortunately you should have done. But um, as I say, these circuit symbols that you are looking at right now are what you just have to learn. There is no other fancy way to say this to you other than um, learn them, and then those questions become really straightforward. So when it says what is a variable resistor, it is this one over here. So A, which is a thermistor. Again, if you learnt it, then a thermistor is this one. You need to know more about these things and what they do, but sorry, it's a tick. But for now, just make sure you know them. In which component will the resistance decrease when the temperature increases? Well, that's where you have to know what these things are. So a thermistor, if you look at the first half of this word, is like a thermometer, but it's not a thermometer. But what it does is it's affected by temperature. So it's temperature related. And so that is the answer for that one. So it's C again, because it's a thermistor. And then in which component will the resistance decrease when the light intensity increases? So this thing here is what's called a light dependent resistor. What that means is it is affected by um, how much light is shining on the object. And that's basically how we can sometimes turn things on when it gets dark and turn them off when it gets lighter, or whichever way around that is. And so the answer to that question is B because of that. Right. Two of these arrangements are in series and two are in parallel. Um, Describe the difference in a series and a parallel arrangement. So a series circuit is basically one loop. Okay, so you have one loop and you can put lots of things on that one loop if you want. Whereas in a parallel circuit, you have lots of loops like this. And then on each loop, you put a different component. So the answer to this question is that the series circuit has only one loop, whereas a parallel circuit has more than one loop. Okay, so a series circuit. Okay, which arrangement has a resistance of 10? So that is a harder question because essentially what you have to understand is that in a series circuit, so let's say that's a series circuit, the total resistance is just all of the resistances added up. So for R, you have 5 add 5 here, which is why that's the answer. But then you should ask me, why is that not the answer then? Because it's also got 5 and 5. Well, it's because in a parallel circuit, the rules are a little bit different. Um, just because of the way, because a parallel circuit is like lots of little separate circuits. And so it sort of changes that answer. So it is a series circuit for that answer. So it is R. Which arrangement has the highest resistance? Well, it's got to be one of these two because that's 10 and 10, so 20, and that's 10 and 10, and that's 20. But again, you might ask me, which one is it? Well, again, it is the series circuit because a series circuit is just as you expect it to be. So if that's 10 and 10, it is 20. In a parallel circuit, there is this weird rule, which for you guys is a bit early to understand this, but the weird rule is that the total resistance of this circuit is less than the resistance on one of the branches. So the total resistance of this circuit is less than 10. The total resistance of this circuit is less than 5, which doesn't logically make any sense because 5 add 5 is 10. So how can the total be less than 5? It is just the way parallel circuits work. So the highest resistance, therefore, is circuit P. And then this should be quite easy, but a student connects a resistor to a cell, use this formula. So as you will find if you stay around for later when I do stuff with year 10 and year 11, when you see these equations questions, you don't really have to understand what is happening. You just need to make sure your maths is good enough to answer the question. So when it says calculate the charge flow, it tells you how to calculate charge flow. You take current, and it tells you current is 0.97 and multiply it by time, and it tells you time is 60 seconds. So you would do on your calculator 0.97 multiplied by 60, You would get 58.2, but then because the answer says two significant figures, you just stop at 58. So 58 is the answer to that question. Is that all of the parts done? It is. So I can move on to question 7. Okay. Right, tricky question this. Um, so in question 7. A householder wants to reduce her electricity bills. The householder takes readings from her electricity meter to see how much electricity she is using. The pictures show the electricity meter readings at the start and end of April in 2013. At the start of April, this is the number that it showed. So the way the electricity meter works is, and you have one in your home, it just shows a number, but that number often goes back like many months and many years, like all of the electricity you've used in like a year or something like that. But so the way they calculate how much you need to pay is they take this number and then they take the number that it's changed to after a month, and then they say, well, the difference between these two numbers is how much you've used in the last month. Okay, so if at the beginning of the month it was this, and then at the end of the month it's this bigger number because it goes up all the time, then the difference between those two is how many we used during that month. So 65,850 minus 65,450 is 400. So 400 is how much we used in April. The householder wants to reduce energy transfer from a room, so she puts a special sheet between a heater and the wall. Um, the side of the sheet facing the heater is shiny metal foil. The side of the sheet facing the wall is polystyrene. The polystyrene contains bubbles of trapped air. Okay, there's quite a lot going on here. This is to do with conduction. What properties of the sheet make it good for reducing the energy transfer? Shiny surfaces are good. Well, you can probably guess this. If something is shiny, what's the best sensible answer here? It is a reflector, right? It reflects things if things are shiny. The idea of shiny surfaces, if you imagine this as a shiny surface on this side, shiny, okay? The idea is that when heat hits it, it bounces off it. So if you have a shiny surface like here, then the heat from here will hit it and bounce off it. And so it'll stay in your room rather than going out of your room. So it keeps your room warmer for longer. And there's another thing. The air is a good insulator. By having little gaps of air, it basically traps the heat better. It's like wearing layers of clothes. Why are two layers of clothing better than just one layer of clothing to keep you warm? It's because you have an air gap in the middle of those two pieces of clothing, and that stops your body heat going any further. It keeps it closer to you for longer. So that is what the answer to that question is. Right. I've also, oh, 7C. The householder turned her thermometer down. Right. So you'd need an equation to be answer this question, and we probably should have given it to you. But I'll tell you what the equation is that you would get given, by the way, in reality. All of you now, recent news has emerged that all of you, regardless of age, will no longer need to learn um, physics equations when you come to do real exams. You should celebrate. Question 9, please, booklet 3. Yes, I'll come to it. So the equation that you would normally have for this question would say something like energy equals mass times something called specific heat capacity, which you don't need to understand for now, times temperature change. If you have this equation, then this should become a very easy question. It says calculate the energy needed to change the temperature of 50 kilograms, that's a mass, 50 kilograms, by 2 degrees. The temperature change is 2, and the specific heat capacity they tell you in the question is 1,000. So you multiply those three numbers together and you get the answer. We do this in our head? 10,000, is it? 100 times 100, yes. No, 100,000. 100,000, sorry. 100,000 joules. Um, okay, and that's that. And then question 5 was also asked. Let's have a look at question 5. The diagram shows information. Okay, this question here is something that you just need to learn, which is your plug socket in your home. There's two measurements for the electricity. One is that the frequency that comes out of our plug sockets in the UK is 50 hertz. And you don't need it for this question, but the voltage of our electricity is 230 volts. But you didn't even need that for this question. Because what you need to try to remember is that frequency is something that is measured in a unit called hertz. And if you know that, then that is the only possible answer to this question. Then the other question also becomes quite easy because if you know that power is something that we measure in a unit called watts, named after somebody, I believe, then you know that that is the only answer to this question. What is the power of the electric kettle? It has to be the one that ends with a W because power is measured in something called watts. I've got a feeling this question will get a bit harder in a minute. So again, you would normally, I need to change these booklets and add the equations in, but there is a formula which says that you get given, once again, charge equals current multiplied by time. So if you have this equation and I tell you to do this question, then you just need to read. It tells you this number of charge, so the charge is 2,400, equals current, we don't know the current, we're going to work it out, multiplied by time. What's the time in this question? 200 seconds. So if I want to work out this value, what do you do from your maths knowledge? You divide this by that. And you should get 12 if you do that. Oh God, there's loads of questions here. Okay. Right, so current equals 12. Then it says, the amount of charge passing through the heating element of an electric kettle depends on the time the kettle is switched on, which should logically make sense. The longer you put a kettle on for, the more charge passes through it. So the more sort of electricity is going through it, right? If it's on for longer, you're using more. So this is a graph that shows how the charge is increasing as time goes on. What's the question? What pattern links the amount of charge? Well, when you see graphs like this, very common sort of questions in terms of understanding the pattern of a graph, all you need to say is that as the time increases, the charge increases, but there's a better answer than that, which is because it's a straight line, what we want to say is that the charge is directly proportional to the time. You can only say that when it's a straight line. What that means is that if one doubles, the other doubles as well. If one triples, the other triples as well. That's what directly proportional means. Um, okay, so, um, and that's question five done, is it not? Yeah. Um, that's question five completed. Just keeping an eye on if this is recording. Um, there's more. There's more. Um, if you've lost it, then just ask for another one next week. Not really, can't really do much about it. Um, in theory, you get one emailed to you as well, so you can always do it in theory. After every lesson, you get the homework booklet emailed to you in case you lose it. That's what the purpose of it is for. Right. Anything else I want to say to you guys? If there are any other questions that from the homework that you have, then feel free to ask me. But in the meantime, I will just go back to this, which I think the students that I taught, the younger ones the other day, I made you draw this out. The reason I made you draw it out was because as I was doing some other GCSE physics exams with other students, there were several questions that just said draw the circuit symbol. And, some people didn't know the circuit symbols. So the earlier that you can just learn what these symbols are, you will be able to do that. Question nine, from which booklet? Three. I think I've done question nine from booklet three. Oh no, I haven't. But I had for some reason. Um, okay, let's have a look at question nine. Oh God, you have to complete these sentences. I've never seen this before. Okay. They've done A for you. The current through a resistor depends on the potential difference across the resistor. Okay, fine. Current, just so we just recap a few things, is how quickly the electricity is flowing around through the wires. Potential difference or voltage is like the force that's coming from the battery that's pushing it around. And so the current, which is how fast it's going, depends on this thing because this thing is the push. If something is pushing you harder, you will move faster. Um, that's that. Right, then let me explain the difference between what's called a direct current and an alternating current, and then we'll see which one the answer is. A direct current is one that only flows in one direction. So it just keeps going in the same direction, round and round and round and round. Whereas an alternating current can, well, it keeps changing direction. It goes one way, then it goes the other way, then it goes the other way, then it goes the other way. It keeps changing direction. Okay, now that we know that, let's see if we are able to answer one of them at least. Well, an alternating current, there's an option here that says is constantly changing direction. So that must be it. Okay. There isn't an option that says that it goes in the same direction, so we need something else. The other thing you should know about a direct current is that batteries supply direct current. So a battery, anything that you have that has a battery, like your mobile phone, for example, supplies a direct current. Whereas things that you plug in to the wall get an alternating current. And so when the question mentions is supplied by a cell or a battery, it is referring to the direct current. So you can just put L there for that. And then in a series circuit, the potential difference, something. Okay, the potential difference is the voltage that comes from the battery. If I've got two bulbs in this circuit, what happens is that they share the voltage from this battery. So for example, they may get three each, or one might get two, the other might get four. But either way, they add up to this. So they're sharing the voltage or the potential difference. So in a series circuit, the potential difference is shared by the components. So that would be that. And then there's only one left. In a parallel circuit, the potential difference across each component is the same. So in a parallel circuit, slightly different thing happens. If I've got a 6-volt battery and I put a bulb like that and a bulb like that, both of them, or both branches, get 6 volts, which weirdly doesn't make sense, but that is what happens. Um, so that is question number 9. Uh, if there's anything else, then feel free to ask. But in the meantime, I will also go back to the importance of these circuit symbols. The other thing that we did a little bit, because there's a lot of things to do in these topics. We talked a bit about the topic of energy, because that was also meant to be although weirdly, there weren't many energy questions in this, were there? Oh yes, there was. There was a few things. There was a few things over here and stuff. So let me just tell you, just as a reminder, when somebody says, when are you going on my booklet? I only answer specific questions from a specific booklet. So when you ask it, I will be able to answer it. So until you ask, I will not go on to it. Right, so other things about the topic of energy that I think are important. Fossil fuels. Um, no, I don't do the other full booklets. I do what people ask me to do. You just don't see the questions. So I answer questions that people ask me to do. Um, So the person that said the website login, if you could send us a message on our WhatsApp or by email, then we will set up that thing for you. It technically already is set up for you. You just haven't used it before. So you just need to ask us for a username and password. So you need to do this, not in these sessions. Send us a message on our WhatsApp or email, and then you will be able to see all of these videos. It's not any topic with questions. It's the topic with videos explaining that topic. That's what it is. So, fossil fuels, there are 3 of them. They are coal, oil, and gas. The things we do with these fossil fuels is we burn them. The reason we burn these things rather than anything else is because they burn really well. That's literally it. There's nothing special about them. They burn really well and give us lots of energy when they burn. and we use that energy. Essentially, the energy just means they get hot, right? But we can use heat energy for lots of different things, such as cooking food, which you do, or heating your home, or to drive cars. Cars basically just burn a fuel, or we can get a lot of our electricity as well from burning these fossil fuels. Not only from those, but we can get a lot of them. Um, right, so that's just a little bit of an intro to these things called fossil fuels. I will come to that question in a second, question two. The other thing that I just want to say about these things, these fossil fuels, when we burn them, there is a gas that gets released into the air. It is carbon dioxide, which is the same gas that we breathe out, but a lot of it gets released when we burn carbon dioxide. And the problem, sorry, we burn fossil fuels. And the problem with carbon dioxide is, very simply put, it basically traps heat. And that means that the Earth starts to get hotter. We call that global warming. So you need to just be have a general understanding of the fact that burning these things is good in that it gives us really important things like cooking, heating, transport, electricity. Imagine what you'd do without it. You wouldn't be on this Zoom call. Um, but the problem is that when we burn these things, then there's this carbon dioxide gas that gets released, which is causing the Earth to get a little bit hotter, which has its own other problems. Let me answer question two um, from this one. Question two, right. A pupil, 2A. Really? Why does the bell not ring? Okay, the bell does not ring because this is not a complete circuit. You can't just have a wire, just sort of loose wires. You have to have a loop to have a complete circuit. So that would be a complete circuit. There's a gap here. This needs to be connected to that for it to work. So it's not a complete circuit. Um, this is not booklet two. This is booklet two, unless I'm missing something. Um, yeah, I'm not confused because that is booklet two. So you have to tell me what you're going on the front of your booklet. If it doesn't look like this, then tell me what it does look like. Right. Okay. So if you are if you did organic chemistry, I can go through that as well. It's just that there's a little timing delay, which just happens to the person who's asking those questions. Which when do you attend and where? Oh, I did miss a Wednesday. That's fine. Yeah, I'll um see if I can go back to that. Um, I didn't miss last Wednesday though. Anyway, um, is this the one you're after? Just out of interest, is this the question? No, it's not. I'm not. I'm doing the correct weeks. Just confirm which city you attended. Are you the person on Sunday in Manchester? Okay. Well, this we did do this last week because that's why it still hits here. So we did all this last week. Hence the answers to these questions are here. So this is not the one that we missed. Yeah, this is not the one we missed. I did this last week. I know I did it last week. I did it last week. So the Sunday that's gone, we did energy and electricity, which is why you remember you drew the circuit symbols. So this is the correct booklet that we are doing. So what you need to be doing is asking questions from this one, which is what you will have got on Sunday. Last Wednesday, I did do this. Anyway, any other questions from these ones? We will talk about it when you come on Sunday. We'll talk about that booklet. Just bring it with you and ask the questions then. I just don't want to do it if it's um yeah, you did. You did do this one. As in you didn't do the Wednesday, is that what you're saying? You did on Sunday, you did this booklet. You did this topic. Yeah. Yes, there you go. So you did. You did this on Sunday. Um, okay, fine. So organic chemistry was a week before. You're a week behind. Anyway, assuming there are no further questions on this. So in terms of the organic chemistry, you can ask, but just do it in person because this is not the you didn't do this. Some people did do organic chemistry at the weekend, but yeah, I know if you didn't do Wednesday, then you can go and watch the YouTube because it will be on there. So we are focusing on what we did most recently, um, which was the energy and the electricity. But on Sunday, when you come, just bring it and make a list of the questions that you don't understand, and I'll spend 5 minutes going through them. Right, assuming there are no further questions on this, I'm just going to quickly just recap the last bit, which I wanted to, which I was in the middle of doing before I got distracted. Um, the other thing to know, just these very basic things about energy, is that these things are called non-renewable energy resources. What that means is once you have burnt some of these things, you can't just reuse them again. They're gone. And then you have to wait for more to be formed, and they're formed over a very, very, very long time. There are other sources of energy that are renewable, like wind and solar, which we never run out of, which are better in the sense that they don't harm the environment. They're not going to run out. But the problem is they're not very reliable because it's not always windy. So you can't rely on this to give us loads of electricity when it is not very windy. Okay. Assuming there are no further questions on the energy and electricity stuff, once more, I'll just remind you, I'll leave this on the screen so you can have a look at it for a while. Um, do try and spend a little bit of time making sure you know these very, very easy marks. And you should not lose any marks on a question that ever says draw a circuit symbol or what is this symbol. Um, I'll leave that on there. Assuming there's no further questions on the homeworks, I will return shortly and go through the year 10 stuff when they start asking those questions. Hello. Yes, if somebody has some energy questions, then I will see what they like and see what I can do. Um, oh, we've already got questions. For a year 10, is it? Sure. So, the year 10s and year 11s, most of you did physics this weekend. I know some people are still on chemistry. We're one week behind with a few people, but this will still be helpful. Um, so the two, three, well, most of the year 10 students did a sort of recap of waves, and you had some questions on waves. Year 11 did kind of a mixture of things like electromagnetism and electricity and something else, radioactivity, I think. Yeah, I think that was sent, but it will hopefully get to you before Sunday, hopefully. If not, then I'll give it to you on Sunday. Um, but the for a year 10 physics. Right, 4A. Um, right. Okay. Um, right. A baby monitor has a sensor unit. Well, the right one's here. No. That transmits an image of the baby and the noises the baby makes to a monitor unit. The monitor unit then displays an image of the baby and emits the noises the baby makes. Compare the properties of the waves that transmit images and noises from the monitor unit. This is asking you for the difference between sound waves, because they're the ones that emit noises, and light waves, because they are the ones that transmit images, right? When you're looking at a TV screen or whatever, it is light that is being transmitted to you. Um, when we're doing terminal exam questions, you don't need to copy up the notes. We just give you what we do in the lesson, but we've technically already done all these topics. So you should have already done some notes on them. So no. Um, so what shall I say about light waves, which are the ones that transmit images? You can say that light waves, for example, are transverse waves, whereas sound waves are longitudinal waves. That's the first key difference when you're comparing them. You can also say that light waves travel faster than sound waves, which is why if you see a firework exploding in the sky, you see it explode and then you hear the sound later because it takes longer for the sound to reach your ears faster. What else can we say? Well, we could have said, well, we've said transverse and longitudinal here, but we haven't explained what that means. So if you wanted to, I mean, you'd probably get all the marks for this, but if you wanted to say one more thing, you could say what transverse waves are. Transverse waves are ones where the oscillations are perpendicular to the direction the wave travels in. Whereas for longitudinal waves, the vibrations or oscillations are parallel to the direction the wave travels in. That's really more than enough for all of those marks. Anything else from in here? Let's have a look at what's been sent over here. Hmm. Okay. Um, what's the question in that one that you've sent me? Anyway, I will do that in a moment. Are there any other questions from any of these bits of homework? Let me have a look what else there is. The type of waves used to send information to and from satellites, we should hopefully know, is microwaves. They're the ones that travel through the Earth's atmosphere. And what happens is the property of this wave is that they can travel through the Earth's atmosphere, whereas other waves bounce off it, and therefore we can't get them to this satellite. They need to travel through this atmosphere to be able to reach the satellite. So microwaves are the ones that do that. Um, no, did not work. Um, oh, sorry. No, there you go. Right. I'll just talk about this question because it's been said, and I'll see what it is. Meanwhile, if you do have any other questions from any of the homeworks, then do say so. But this is a question that is related to physics. A child drops a ball, the ball hits the ground and bounces. The graph below shows the velocity time graph for the ball when the ball is dropped until when the ball reaches the top of its first bounce. So we drop it, and then it suddenly hits the ground. Then it's traveling again. Then it reaches the top of its height, and then it comes back to a stop. Okay, fine. I can understand what's happening here. The question is, when the ball hits the ground, energy is transferred from the ball to the earth. Explain how the data shows this energy transfer. Um, okay, so I think what you need to say is this part of this graph is when the ball is dropping. No, yes, dropping to the ground, dropping to the ground, dropping to the ground, dropping to the ground, dropping to the ground. Then it hits the ground there. How do I know it hits the ground there? Because as soon as a ball hits the ground, what does it happens to its speed for a moment? It suddenly stops. And so that velocity comes back down to zero. So it's stopped, right? Just in that moment, just as it's hit the ground, it stopped. Then it bounces up again. And then when it reaches the top of its height, so imagine this is the ball and there's the ground, it goes up. And then here, it stops again. Just when you throw a ball in the air, just at the top of its height, it stops for a moment. And so here it has stopped, and then, oh no, it's not actually stopped. Ignore that. It's not stopped again. Um, it then reaches the top of its height, and then it starts to slow down again. So wait, I'm trying to understand what's happening. It stops, then it starts moving again, and then it slows down again. Fine. Okay. The way this graph shows this question. Oh, velocity is negative when things travel in the opposite direction. So because velocity is a vector quantity, it means that it can be negative if things are going in the opposite direction. So this ball, effectively, if this is the ground, we drop it, it hits the ground, and now it's going the other way. So when it's going the other way, we represent that with negative velocity. So that's why it's negative now. And then, it's confusing this, then it gradually, so when it bounces, it's then going at a certain speed, but then it slows down again as it reaches the top of its height. So here it's at the top there. So how do I know in this question? The question is, explain how the data shows the energy transfer that when the ball hits the ground, energy is transferred from the ball to the earth. So at this point here, right, the ball is traveling at its fastest speed. Okay, so it's got a lot of kinetic energy when it's moving. Okay, then it hits the ground and then it starts moving again. But you see, when it's moving again, it is traveling at a different speed. So this was about 7, and now this is about -5. So just ignore the minus for a minute. It's 7 there, and it's 5 there. So it has obviously lost some speed and therefore lost some kinetic energy after bouncing. So that's the answer essentially, because some of the energy when it's hit the ground there has been transferred to the earth. It just makes the ground warm up a little bit, and it heats up the ground a little bit due to friction. And so now it doesn't have as much kinetic energy, which means it doesn't reach as high a speed. I know it's negative, that makes it confusing, but it's just going the opposite direction. But what you're doing is comparing the fact that its speed here is about 5, and here it was about 7. So it's lost some speed after bouncing, and that proves that some of the kinetic energy has been lost somewhere and it's to the ground, essentially. That's it. That's how the graph shows it. Don't know how to get all of the marks for that. Yeah, I think you put some numbers in and you'd be fine. Fine, that's it. Right, okay, given that there are no further questions, I'm going to continue going through some of the waves part of this. Go through this. Jeez, okay. I won't do that. Okay, this kind of thing is it's important. It's the sort of thing that people get wrong with this kind of stuff. Your electromagnetic waves go. Yes, I'll do that in a second. So they go radio waves on the far left, then microwaves, then infrared, then visible light, then ultraviolet, then X-rays, then gamma rays. You need to be comfortable with that order. You also need to be comfortable with the fact that the wavelength is the longest on this side and shortest on this side. So we have short wavelength waves here and long wavelength waves here, but frequency, which is the number of waves per second, is highest over here because they're so close together, whereas here it is a low frequency. So once you get that in your mind, then this kind of question becomes easy. How do X-rays compare with gamma rays? The first option is X-rays have a longer wavelength and a higher frequency. No, they don't. Oh, they do have a longer wavelength, but they don't have a higher frequency. Um, they have a longer wavelength and a lower frequency. So as we go this way, the wavelength is decreasing, but the frequency is increasing. So as we go that way, your wavelength is getting longer, but the frequency is getting lower. Quite awkward, that kind of question. Um, I will just move on to the year 11's mix and match here, which is that some of you had a few topics to do with electricity, radioactivity, and electromagnetism, um, which some of you in year 10 haven't done all of yet, but you may have done. Um, right, yeah, that's an awkward question, that one that you just asked. I remember it. So, first, I'll just go through the whole question quickly. The ammeter displays a reading of 0.1 amps here. This is a series circuit, as you can see. Calculate except the switch is weird here because I've put the switch there, which I'll explain what happens there in a minute. Calculate the potential difference across the 45 ohm resistor. So, well, what you're supposed to know is that in a series circuit, the current is the same for every component. So if I know what the current is there and what the resistance is there, then the formula V equals IR tells me that the potential difference or voltage is 45 times 0.1, which is 4.5. That is the voltage across that resistor. Calculate the resistance of the resistor labeled R. The only way to do that, oh, there's two ways to do this. The quickest way to do that is to work out the total resistance in this circuit by doing the voltage divided by the current. The voltage is 12, the current is 0.1. That gives you a total resistance in the circuit of 120, which has to be split among these resistors. We've got 60 and 45 there, which is 105, leaving you with 15. There is another way to do that, but I won't go into that. Okay. State what happens to the total resistance and the current through the circuit when switch S is closed. Okay. The answer to this question is that when you close switch S, the total resistance in the circuit decreases. And when total resistance decreases, the current increases. Essentially, the way I think of this is that when you add more wires to a circuit, effectively like in a parallel circuit, if you add more branches, you're increasing the current in the circuit because current just needs different is how many is the paths that it can take. So you can take this path and then this path and then this path. So you're actually increasing the current in the circuit. And if current is increasing, then resistance is just the opposite of that. So current increases, resistance decreases. There is a sort of another explanation for that. In like a parallel circuit, the total resistance is lower than the resistance of any one branch. So that's like an extra branch. And me, by closing this circuit, I've sort of created another branch, and the total resistance has actually decreased as a result. Um, so the total resistance decreases, but mainly understanding the current increasing gets you there, which is that if you add more wires to a circuit, the total current um, increases. Or if you add more branches to like a parallel circuit, then the total current increases. And 5C, and I'll do all of 5. Sam and Chris are arguing about alpha and gamma radiation. Sam says alpha is more dangerous. Chris disagrees. He thinks that gamma is more dangerous. What do you think? Explain your answers as fully as you can. The answer to this question is essentially always to do with whether we're talking about inside or outside the body. No, the current doesn't get shared. The current overall, the current does get shared, but it increases and then it's shared. Essentially, if I have this circuit here, okay, then there is a current in this circuit, a certain value for the current. But if I now add another branch to that, the total current in this circuit has increased. If I add another branch to that, the total current has increased again. It is still shared between these components, but the total current has increased. So for example, if it was 0.2 amps originally, then adding another branch basically means that now it's going to be 0.4 amps because some of it will go this way and some of it will go this way. And then adding another branch will do the same thing. So it'll increase the total current in the circuit. When you come to alpha, beta, gamma, and I ask this question when I teach people, I basically say, which one's the most dangerous of the circuits? Which one's the most dangerous? The answer is always to do with whether you're talking about inside the body or outside the body. So alpha is dangerous if it gets into your body, right? So if it's inside your body, alpha becomes the most dangerous because it is highly ionizing. It can cause cancer and damage your cells. And it also can't get out because it's so not very penetrating. If it's made it into your body, then it's not going to be able to get out easily. Whereas if you've got, some radiation outside your body, if you're standing here and there's radiation coming towards you, then alpha is not really that dangerous because it is not very penetrating. Gamma becomes more dangerous if you've got it coming towards you from outside your body because gamma is more penetrating and it can therefore get through your skin and reach your cells and organs if it gets through your skin. So understanding that there's no simple answer to that question, hence this question. How would you explain that to get the marks? What I wrote essentially gets you both marks, which is because it just says state what happens. It doesn't ask you to explain it. It just says state what happens to the total resistance. So you're going to, well, it says state what happens to the total resistance and the current. So you're going to say something goes up, the other goes down, or something stays the same. You're not asked to explain it. It's very important that when you read these questions, you don't do more than what it asks you to do. So it only says state what happens. So the current increases, the total resistance decreases. That is all the 2 marks that you need for that, for just stating it. Okay, that was 5A. 5B, cancer cells can be killed by injecting a radioactive substance. What other features must the radioactive substance have to make it suitable for this job? Okay, if you are injecting a radioactive substance into somebody's body, then firstly, you want to make sure that that radioactive substance is emitting gamma radiation. Because for what I just said earlier, if alpha gets into your body, then it stays in your body and it can cause a lot of harm. Whereas, wait, I got that wrong. Sorry. Cancer cells in your oh no, sorry, it's not that. It's because we're trying to kill the cancer cells, right? So because we're trying to kill these cancer cells inside your body, then the only way to do that is to use a type of radiation that is highly ionizing. That's what ionizing has the ability to kill cells. So what we need to do is to make sure that it's a highly ionizing form of radiation, and that therefore has to be alpha. It must emit alpha radiation, which I appreciate goes against what I said earlier, because alpha is the most dangerous inside the body. But we're trying to kill certain cells here, cancer cells, so we have to use this. But the way we have a precaution is by ensuring that we have a half-life that's short. Half-life is essentially how long it will continue to give radiation out for. Um, a short half-life, but long enough to kill the cells. You don't want it to be very short, then it can't do anything. So it's a very dangerous thing to do to put this radiation in your body, but you kind of have a precaution by using something that has a short half-life, which means it very quickly stops giving out radiation. You don't want to be giving out radiation for months and years. It should be only for a short period of time, enough to kill the cells. Um, Radon is a radioactive gas with a half-life of 3.6 days. I was teaching in the building. Estimate how long it takes for 99% of a sample of radium gas to decay. Oh, jeez. How would I do this? Um, okay, that's quite a hard one to get right. So essentially, what that means is that every 3.6 days, the radioactivity halves. That's what it means. So if it started on 100, for example, just as using 100 as an example, I think I might use 100. That might work. In fact, it does work. It works perfectly well. Because essentially, if I start with 100, then how long it takes for 99% of it to decay, that means we want to end up on 1, don't we? That's 99% of it has gone. So if I halve this, then it would be 50. If I halve it again, it's 25. If I halve it again, it's 12 and a half. If I halve it again, it's 6.25. I need to keep halving it until I drop below 1, basically. If I halve it again, then it's about 3.1-ish. If I halve it again, then it's about 1.5-ish. I know it's not exactly. If I halve it again, then it has dropped below 1. So we've got rid of 99% of it in that process. How many jumps did I do there? 1, 2, 3, 4, 5, 6, 7. That means that's 7 half-lives. So it's taken 7 half-lives for me to halve this number enough for it to end up being less than 1% of what it started with. A half-life is 3.6 days. So if you do 7 times 3.6, that means in real time, it will take about 25.2 days. Or slightly less than that, because I've dropped to 0.75. But that would be the only way to do that. You have to sort of go through the halving process and see how many times you have to halve this number until it is 1% of what it started with. Okay, I'm just going to go back to some other questions on the waves because that would be applicable to everybody. Um, this kind of thing, again, very important. Just be familiar with this entire thing. Which letter shows the position of ultraviolet radiation within the electromagnetic? So again, if you know this, you know that radio goes there, infrared goes there, ultraviolet goes there, and X-rays goes there, which means you've got the position R. Again, that's why it's important to learn this. In the vehicle diagram, if you increase the potential difference in the current, what will happen to resistance? Well, in theory, it would have to go up as well. No, no way. If you increase the voltage and the current, um, well, it depends on how much by you increase it by. I don't think it's quite as simple as an answer. Because if I said to you 10 equals 5 times 2, I could increase that to 20 and I could increase that to 10, which means that the resistance doesn't change. So I don't think it's quite as simple as there is a one answer. There's no one answer to that question. It just depends on how much you're increasing it by. Here I've increased both of them and the resistance has not changed because it still works as a formula. So it kind of, yeah. A better question would be like, if one of them stays the same and the one increases, what happens to the other? That's normally how this normally works. Um, Again, same sort of thing, which is why I said that thing about knowing the wavelength and frequency stuff about these. Um, so ultraviolet radiation, which two statements describe the electromagnetic wave emitted by an ultraviolet lamp? Do they have a higher frequency than X-rays? No, they don't, because X-rays are to the right. They have a higher frequency over here. Do they have the same wave speed as visible light? Yes, all of the electromagnetic waves, the whole point, the reason they're grouped together is that they all travel at the same speed in a vacuum, but that's the same thing. Do they have a longer wavelength than microwaves? No, they don't. The longer wavelengths are this side. So microwaves have a longer wavelength than these ones. They have a lower frequency than gamma rays. Again, gamma rays have the highest frequency, so that's not the answer either. They have a greater wave speed. Oh no, wait, which one is the answer? Which is two boxes? Sorry, I've made a mistake here. Which two seem to describe the electron? I've missed something. They don't have a higher frequency. We're talking about ultraviolet, aren't we? So they don't have a higher frequency than X-rays. They do have a lower frequency than gamma. Sorry, yeah, they have a lower frequency than gamma because gamma is the highest one. Um, they don't have a greater wave speed because they all travel at the same speed. That is the point of all of this. So, um, that question, which says if resistance is the same and current increases, then does voltage decrease? Based on this formula, yes. So if resistance stays the same and um, current increases, then voltage decreases. But there is another complicated part of that, which is to do with transformers when you have. But yeah, in answer to your question, yes, if resistance stays the same, and wait, let me work this out. It's the same. So V equals I times R. Um, let's say just make a calculation like 10 equals 5 times 2. If that stays the same, and you're saying current increases, let's say that increases to 10, then yes, voltage has to, but voltage would increase then, wouldn't it? Based on this formula. I know what you're asking. I think you're confusing something else. I know. But based purely on that formula, if that goes up, then that has to go up as well. Because current, remember, is just how fast the electricity is flowing. If that's gone up, then voltage has gone up. But what you're thinking of is another formula, which is this one, which basically says that if power stays the same, then if current goes up, resistance has to go down, or voltage has to go down. And that's what happens when you use a step-up transformer. You increase the voltage to a really high level, which decreases the current because it's on the assumption that the power stays the same. Resistance will change as well, but we're not looking at that in that formula. So it is a little bit nuanced, but what you need to know is this equation tells you that if current goes up or voltage goes up, then current goes down, assuming the power stays the same. But power is also linked to resistance, which is why it all gets a bit complicated. But for the purpose of understanding transformers, when we step up electricity, we increase the voltage to lower the current because this formula tells you if you increase the voltage, you will lower the current. So it is a little bit confusing, I understand. So, as I said, for the Transformers question is the one where you need to focus on this one here. Because when you have to explain how a step-up transformer works, that's the thing we're looking at. That's the thing. Step-up transformers work because we increase the voltage, which lowers the current. So that's how we have to explain that. 'Cause that's what we're trying to do. We're trying to get the current low so it doesn't get very hot in the wires and we don't waste energy. Depending on the question, in other cases, you might need, most other questions, anything else, will probably be dealing with that kind of thing. So you don't always know. That's what makes it a bit harder. But usually, as I will demonstrate when we do loads of calculation questions are just not that particularly scary when it comes to physics exams. You just find the formula, which you get anyway, and you do it. But you're not talking about calculation questions, you're talking about explaining it a little bit more, which I understand is a bit more complicated. Um, but we will just get through as many practice questions as we can in the meantime. Um, Just seeing if anybody has any other questions from the various homeworks that you might have had. Some people have still been doing chemistry at the weekend, so if you do, then let me know. Um, Okay, I'm just going to switch over a little bit now. I know we've been doing physics, but there are a few questions I want to just demonstrate for you that I was doing the other day, just to show you how physics equations questions are not always terribly challenging. Okay, so what I've done is open up a physics paper, triple science this is, but it doesn't really matter because I'm looking for the equations, um, from 2024. Okay, stuff like this. I mean, it's very, very easy marks, this stuff, so we should never fear this stuff. The only thing you have to be careful of is units when it comes to physics questions. The units are where you will lose marks if you're not careful. So you look at the equation sheet and you find the equation that links energy, power, and time, which I can tell you is energy equals power multiplied by time, or power is energy divided by time. Let's say a version of those two. Then a nuclear power station has a power output of that. Calculate the energy output. So calculate energy. The formula is energy is power multiplied by time. The time is 3,600 seconds. And I ask you for the power. The power, though, has been given to you in a unit that is megawatts, capital M. Try to make sure you remember that a capital M is a megawatt, which is basically a million. It's easy to remember a million in that situation. So we actually have 500 million watts here. That's how you could get this wrong, because you don't convert it correctly in this kind of question. So let me try to go back to that question. So it's this one you're asking me about, isn't it? So, question 14 that you did before, that doesn't follow because the current increased when resistance increased. How did that work? The current increased when the resistance decreased. Um, that does make sense though, because the formula is V equals IR. So we are assuming the voltage stays the same. So if that goes down, then that has to go up because the battery is still the same. So we've got a 12-volt battery here. So that does make sense, I think, based on that formula. If the resistance goes down, the current would go up, wouldn't it? To keep the number the same here. So for example, if it was 12 equals 6 times 2, for example, and I say that's gone down to 1, but that stayed as 12, then this has to go up to 12. So in that sense, that does work, I think. Yeah, so that same thing, isn't it? Resistance decreased, current increased. So they're just opposites of each other based on that formula. If one's going up, the other's going down. Current increased when the resistance decreased. That's what happened, right? Yeah, exactly. So yeah, that's what happened, which does follow, I think, because we're assuming that number stays the same. If this goes up, then this goes down to keep that 12 same from the battery. Um, I said they'll both increase. No, wait, I think we're confusing different things here. But let me see where I was talking about that. But we're talking about different things. Here we were talking about voltage and current. Now you're talking about current and resistance. So you're talking about different things because they're in different places in the equation. Here we were talking about resistance staying the same, and voltage we were talking about voltage and current. So we're talking about different things. in that question. Right, what was I doing? Yes, I was doing something on the physics equation, the physics paper. I just want to do one more calculation question because I'm pretty sure there's something in my head that was challenging. Yes, I'm just going to do this question. So, this question shows you've probably seen some of these things where you can sort of get in a pod and then it stretches you down and then lets go of you and you fly up. Right, that's the kind of thing that happens here. Um, the question here is saying that when the pod is released, so if I let go of this here, when I've stretched it all out, it will fly up there um, and it will accelerate upwards. Before the pod is released, the extension of each of the two bungee cords is 8 meters, so we stretch them 8 meters. The spring constant is this, the mass of the pod is this, that is this, calculate the height. So there's a lot of information here, right? Loads of information. But let me explain to you how you would go about doing these 6 mark questions. You should hopefully realize that when you stretch things out, they have what's called elastic potential energy. Mm. Mm. Okay. Yes, elastic potential energy, which has a formula that you get given, which is a half times spring constant times extension squared. That's what the formula is for elastic energy. So what I can do is I can work out how much energy there is in these bungee cords in this question, how much energy they have before we let go of them, by doing a half times the spring constant, which is 735, times the extension, which they tell you is 8 squared. But you got to remember, this is the extension in each of the two bungee cords. So there'll be twice as much energy. We're pulling with two of these things. I'm going to times that by 2 as well. That tells me that this is the amount of energy I've got. 0.5 times 735 times 8 squared. That would be in one of them. So in two of them, it is 47,040 joules of energy. But that's not the question. The question is, calculate the maximum height reached by the pod. So when you let the question's gone. When you let go of this, the thing jumps up and ends up really high up in the sky over there. How can we work out the height that it has reached? Well, we can use a different formula, which is to do with gravitational potential energy. Because this formula is mass times gravitational field strength times height, crucially. If I know how high something is, I know how much gravitational energy it's got. If I know how much gravitational energy something has got, I should be able to work out how high up it is. And so what we do is we understand that when you let go of that cord, the elastic energy in this is converted to gravitational energy as this is going up. That's what you have to understand. There's an energy transfer here of elastic to gravitational. And we assume at the highest point, all of this elastic energy has turned into gravitational energy. So I put that as the amount of energy. That's the most amount of energy it could have. And then we just fill in the blanks. The mass of the pod is 240 kilograms, it tells you in the question. The gravitational field strength, it tells you in the question, is 9.8. So everything you need is in there. And then I can work out what this h is by dividing these two things to the other side. 20 from memory. 20 is the height of that. That is a 6 mark question, which is really just two equations that you have to use. Um, right, going back to this, 9b part 5. Okay, right, I've got a feeling this is going to be very complicated to explain, but let's do my best. Okay, I'll have to just go through 9 briefly. So this is potentially divided by cells, the total resistance of the circuit. The name of this component is a filament bulb. That is the shape of that. Um, 6 volts, isn't it? Yeah, 6 volts is like a parallel circuit. Um, the resistance of X, if it's getting 6 volts, then resistance is voltage over current. 6 divided by 2 should be 3. That was 3. The current in Y, well, if there's 3 amps here and 2 have gone there, then only 1 can go here. So it's split into 2 and 1. The resistance of Y, that will also get 6 volts. So it's 6 divided by 1, which is 6 ohms. Okay, so that's all that done. All right, let me see if this makes sense. Um, when the temperature of resistor X increases, its resistance increases. What would happen to the potential difference across X? Okay, well, when the resistance increases, um, the current will just decrease. So the potential difference will stay the same. Um, because what's happening here is that the resistance of this is going up. And all that does is it means that a different amount of current has to come here. This never changes. This is a parallel circuit. Every branch gets 6 volts. That doesn't change. So the potential difference will stay the same. But because the resistance has increased, that's what it says in this question, right? Resistance increases. Because the resistance of this is increased, um, there will be more current going towards it. Because you can just do this as a calculation. They said that the resistance of X, or it was 3, wasn't it, before? The reason it was 3 is because it was 6 divided by 2. Now, if I say that that becomes 4, or make it 6, let's say, well, then surely that has to change to 1 for this to work, right? Because resistance is voltage over current. And so if I'm saying that resistance is increasing, but voltage is staying the same, that can only happen if the current goes down. If the current goes down, then the resistance will go up in that situation. So the current goes down, um, and the total current in the circuit. Oh, okay. If the resistance, let me work this out. Oh, well, it would decrease, wouldn't it? Because if that suddenly decreases to 1, this doesn't change at all. So if that's 1 and that's 1 now, hasn't the total current decreased as well? That's how you're supposed to go about this question. It's a very complicated question, but that is what it is. The total current would decrease because the branches current have decreased, and so the total has to decrease. Quite complicated, these parallel circuit things. Right, last one then I will do, and I'll call it for today. Is there anything else exciting in here? Yeah, this we can do on its own, I think. So without reading any other parts of this question, we should be able to get all of the marks on this kind of question. But there's one problematic part of it. This is more math than physics, to be honest. Right, there is a formula involving density, which is density is mass divided by volume. If the question says work out mass, it's going to be density times volume. Right. Then we have to look at the units and everything that's given to us in the question. The density is 21,500 kilograms per meters cubed. And that's where the problem is. Because this is in meters cubed. The volume is not 0.44 because we don't want to use a different unit here than we have here. So we need to convert centimeters cubed to meters cubed. Does anybody know how many centimeters cubed are in a meters cubed? The answer is not 100. in case you don't know, I shall tell you the best way to do this. So let me see what the answer is. 10,000. No, not 10,000. I'll tell you, a million is the answer, correct. So the best way to do this, if you are unsure how to do this, since if it comes up, because usually everybody knows there are 100 centimeters in a meter, right? We all know this. But generally, if I then say to you how many centimeters squared are in a meter squared, or how many centimeters cubed are in a meter cubed, you are less confident with that answer. The way to do it is to go, well, if the question was about centimeters cubed, let's say, and meters cubed, then effectively what we're doing, sorry, squared, let's do squared first. Effectively, we're just squaring everything that you see here. Now, 1 squared is just 1, but 100 squared has 2 more zeros after it. So it becomes 10,000 centimeters squared. So in 1 meter squared, there are 10,000 centimeters squared. If we did the same thing for cubed, which we have to do in this question, just cube everything. So 1 meter is 100 centimeters, but 1 meters cubed is 100 cubed, which is 1 followed by 6 zeros. So it is 1 million centimeters cubed. So if I want to convert centimeters cubed to meters cubed, sadly, I have to divide my answer by a million. And that's what I've got to do with this number. I've got to divide it by a million to make it meters cubed so it matches the units over here. Yeah, it'll tell you something like that. Just write that down. 4.4 times 10 to the minus 7. So that is my density. That is my volume. So if I multiply that answer on the calculator by 21,500, it will work out the mass in kilograms. And remember, when you do these things and the calculator gives you it in standard form, if it's in science anyway, write the answer as it appears on the calculator. In maths, they might say write it as an ordinary number, and then you have to convert it back to 0.0000946 or whatever. But in science, just write the final answer. I think that will be sufficient for today. If you have more questions, then please feel free to just send them as and when. Reminder, again, I'll keep saying it because it gets closer and closer to the time. From the 1st of May onwards, I will be doing one of these every day, basically. But if you have stuff before that, if you panic before that, then you feel free to contact us. You know you can regarding anything. But from 1st of May onwards, there'll be one of these every single day. I think it'll be at 7 p.m. every single day for about 6 weeks. Should you have any questions in the lead up or during your GCSE exams or otherwise for younger people. Right, I think that's enough for today. Any questions, do let me know.